Got it? All right. Let's begin with a word of prayer. I will start. Dear Father, we thank you for this day. And again, Lord, I thank you for this opportunity we have just to meet together and talk openly about your creation. We thank you that you love us like you do, and we thank you that you died for us to forgive our sins, even though we don't deserve it, Lord. And we thank you that we can have your righteousness instead of our own if we just accept you into our hearts. And I just pray you be with us today. Just guide this class and bless it to your purposes, Lord. In your name I pray. Amen. Okay, so get right into it. I know some of you are sad because you just finished a linear homework and then there's not another one to work on. But rest assured that I'm working on it. So I will have another one. Because I know your life is not really complete unless you have a linear algebra homework to work on. I know that. I accept that. So I will give you another one soon, don't worry.
Define soon.
Today?
Okay.
Probably. So we are now talking about linear transformations. Now, so first things first, let me give you a definition. Basically, a linear transformation is a function which is natural to the subject, to the study of linear algebra. It's a function which preserves the linear structure. So here's the definition. Let V and W be vector spaces over a field F. So we can use this notation to quickly denote that, like V of F means it's a vector field. Listen to me, vector field. Vector space over a field F. W is another vector space over a field F. Then T, a function. All right, so this notation means functions. Function from V to W, right, is a linear transformation. Linear transformation. If you have two following things. Number one, you have additivity. So we have T of x plus y is T of x plus T of y. That has to happen for all x and y in V, in the domain. And so that's additivity. Additivity is one requirement. Homogeneity is the other requirement. And here's where the field comes into play. The definition for homogeneity depends on the field in question, but basically this means we can pull out a scalar like so. And that has to be, here. This is for all x in V and C in the set of scalars, the field. So there you go. A linear, both of these, if a function has both of these properties at once, both of these traits at the same time, then it's said to be a linear transformation. And I also refer to when you have 1 and 2, if you have both 1 and 2 together, I'll say that a function is linear. Or it has its linearity, as I'll refer to that in calculus. If it has both of these things, you can break up sums and pull out scalars. So what are some examples of this, right? I guess the better question is what's not an example of this. So here's a non-example for you. How about this? T from the reals to the reals such that T of x equals to, I don't know, pick your favorite function, almost any function, sine of x. This fails to be homogeneous and additive, right? It's certainly the case that, sine of x plus y is not equal to sine of x plus sine of y, right? And also the sine of cx is not equal to c times the sine of x, right? This function sine is neither additive nor homogeneous. What are some other examples, non-examples we could think of? How about this? What if I had this? I don't know. How about T from R2 to, I don't really need R2, but I'll do R2 to R. And let's say T of x comma y is equal to x squared plus y squared. It's a function, right? It's a single valued assignment of each pair of real numbers to a given real number output. So it's a function, that much is true, but it's definitely not a linear transformation. Again, it fails to be both what? Additive and homogeneous, yeah. So what do we have? We've got like, I mean, you can see it. I'll just do the homogeneity. So here, if I have c times xy, that's what? Cx comma cy, right? Which is cx squared plus cy squared, which is c squared times t of xy when you work it out, right? So apparently this function has a kind of modified homogeneity. You can pull out the square of a constant, but not a constant. It's actually an interesting example for later in the course, but anyway. Enough non-examples. What are some actual examples? How about this? If we look at D, I'm mapping from, let's say, R of t to R of t, where these are, of course, the polynomials in t, right? And our definition is D of f of t is equal to f prime of t. Is this a linear transformation? So let's see here. Let's be greedy. D of c times f of t plus g of t is equal to what? By definition, cf of t plus g of t prime, right? But we know how prime works because we took calculus. This is c times f prime of t plus g prime of t, right? By calculus. And that is, well, there you go. That's d, c times d of f of t, right? Plus d of g of t. So we can be greedy and use this one calculation to, at the same time, get what? Linearity, and I mean, we can get linearity from this, right? We can get homogeneity and additivity. How do you get homogeneity? Take g of t equals to 0. We obtain 2, right? Homogeneity. If we take c equals to 1, we obtain additivity, right? Just to be clear, x, quote unquote, is the f of t, right? Y, quote unquote, is the g of t, looking back at the definition. This kind of abstraction is always at play in here. X and y are arbitrary vectors in an abstract vector space. Those could be polynomials. Those could be matrices. I mean, there's tons of examples, as we've seen, right? Okay. You could easily, can you guys see anything I could do with this example? Does the domain of the differentiation operator just have to be polynomials? If it's Math 126, that's almost the case. But even Math 126, we can differentiate algebraic functions. So certainly you could at least expand this to the set of algebraic functions. If the derivative of an algebraic function, to get an algebraic function? Yeah. So you could look at the differentiation operator as a linear transformation on any set of function which is closed under differentiation. Right. So you could easily replace the polynomial R of t with, say, smooth functions, right? And what else could we do? I mean, there's other examples. You could do like, how about this? I won't work this one out, but you could do something like t is equal to d squared plus 3d plus 7, where we're saying t of f of x is equal to f prime prime of x plus thrice f prime of x plus 7 times f of x. This would be a linear transformation on functions defined in terms of a second derivative, a first derivative, and just multiplication by 7. All right. You can also prove that that's a linear transformation. So, goodness gracious, I mean, you can take arbitrary like compositions of derivatives, multiplications by numbers, right, of functions. These give you linear transformations. All right, here's a important example. T of, let's say, x comma y is equal to 3x minus y, comma 2y, comma x plus y. Does this define a linear transformation? So here t is a mapping from what? From R2? I guess it's not clear. You could say it's from R2, you could say it's from C2. I mean, it's kind of up to you. I'm going to say, though, it's from R2 to R3, just to keep it real. I make no apologies for that pun. Let's see here. What's that? That wasn't an apology. I was saying I say I'm keeping it real without apology. Let's see here. If I was to make an apology, it would, well, I don't know. Trump has taught me that I shouldn't make apologies. Let's see here. So 3 minus 1, 0, 2, 1, 1, xy. See what I did? Matrix multiplication, yeah. So I'm going to kind of like, I'm going to take an indirect approach to showing you that this is a linear transformation. I'm going to use matrix properties to do it, rather than just plugging in and slogging through x1, y1, and x2, y2. Right? There's a better way to think about this, which is write it as this formula, give this a name. Let's call it A. Right? So what we really have is t of v is equal to a v, where v is the vector xy, right? And then linearity of t is a walk in the park, right? I mean, it's easy, not a problem. It's not a. I guess some parks is kind of dangerous, like where we used to live in Durham, North Carolina. Walk in the park could be like the last walk you take. See here, t of. It's dangerous. I mean, let's see here. What was I going? Oh yes. So how about this? V plus w. Oh, good. Phew. Okay. We lost power this morning. Now we've got it back. Woo-hoo. All right. So this is a times v plus w, right? Which is what? AV plus AW by properties of matrix. Column vector multiplication, which we have already worked out and are free to use. And that is T of V plus T of W. Bam. Additive. Right? That holds for arbitrary V, consequently arbitrary x comma y, so we have additivity. And goodness gracious, why don't we be lazy and do homogeneity at the same time? C, pull the C out, C. There you go. We have linearity, hence additivity and homogeneity all at once. All right. So basically, if we have a function that's going from, say, some copy of column vectors to some other copy of column vectors, if you have a formula which is built from a linear expression, a linear combination of the domain variables for each range component of the function, then you can rewrite that as a matrix multiplication and you'll have linear transformation. So I mean, this is a little theorem here, basically, we can state, right? Theorem. If T is a mapping from, say, R, let's be greedier. Let's be greedier. From F, Fn to Fm, and T of V is equal to AV for some A in Fm by n, then T is a linear transformation. Now, let me say that more lazily. T is an element of L of Fn comma Fm. One of the things I neglected in this definition, for shame, is what do we call the set of all such things? T is an element of L of V comma W. Here's our name calling. This is L of V comma W is the set of all linear transformations from V to W. So that's just to give T a home. That's where it lives. Set of all linear transformation L V comma W. Es bueno? Yeah. So what's the proof of this theorem? It's kind of like this calculation right here, right? What's interesting is, while I've stated this as an if-then, the converse is also true. Okay, the fundamental theorem of linear algebra says, in fact, every linear transformation of column vectors over a field can be written as matrix multiplication. So this can be reversed. If T is a linear transformation from Fn to Fm, then T has a formula which is just matrix multiplication. That's called the fundamental theorem of linear algebra. Although it seems like a bit much as a title. All right. I have more examples in the notes. I'm going to go on, though. Unless there is a question. I'll tell you what, well, it's not time to, I don't want to prove that fundamental theorem of linear algebra just yet, because we need a few more properties to make it easy. It would be a lot of work right now to do that. I will tell you this much. This A, it's not an innocent bystander. There's a special notation we have for this. We say that A is equal to the so-called standard matrix of T. So this is the so-called standard matrix of T. And now I may or may not have time to say more about that today, but rest assured that's something that you want to learn about. Standard matrix of T. Okay. So those brackets are, you know, there's a lot hidden in those brackets. All right. So let's work out some basic properties of linear transformations. I'm going to start at the beginning, and we're going to work our way through all of the essential fundamental theorems for linear transformations. The first of those, I would say, is that a linear transformation maps 0 to 0. So let T be a linear transformation. If you have T, an element of the linear transformations from V to W, then L, listen to me. T of 0 is equal to 0, and 2, oh man, I still have L in the notes. I was trying to change all these L's to T's. I missed proposition 13 and 14. I mean, it's not a big deal. I've got it written in terms of L in the notes. I'm going to switch that over to T right now to try to be kind of consistent. The other thing is the linear transformation of a linear combination is the linear combination of the images in the same way. So linear transformations respect linear combinations in that sense. Okay, so that's our first two orders of business. So how do we prove one? So let's see here. Any ideas? I'm assuming you haven't read the notes. For once, I hope you haven't read the notes. Any ideas? I mean, if you read the notes, it's kind of boring. You already know the answer. It's in the notes. What makes 0 0? Zero plus 0 equals what? Right. So how about this? T of 0 is equal to T of 0 plus 0. But additivity gives me what? This is T of 0 plus T of 0 by additivity, right? So consequently, T of 0 is equal to 0. Just subtracting T of 0 from both sides up there, or using the cancellation property if you remember that. So there's one. That was kind of non-eventful. But that's, by the way, a good way to strike down something as not being a legitimate linear transformation. If you can show that 0 doesn't map to 0, game over, done, not a linear transformation. So that's kind of a nice thing to know about. But there's lots of examples like that x squared plus y squared example where 0 will map to 0, and yet it's still not a linear transformation, right? So that's not enough, but it's part of it. 2, let's see here. This is a claim about what? To be more precise, this is for what? For all n in the natural numbers. So this probably is something we should prove by induction, right? So let's proceed by induction on n. So first of all, n equals 1. We have t of, well, cv is equal to ct of v. That's the n equals 1 case. Sorting, I mean, when you go back to how we defined finite sums of one thing, that's the n equals 1 case without being overly formal. That's n equals 1. That's automatic. And n equals 1 is homogeneity, so we have it. So suppose inductively then. Suppose inductively that t of a sum I equals 1 to n of ci vi is equal to a sum I equals 1 to n of ci t of vi for some scalars and for some vectors in the domain, which here was v. And then consider what? Actually, it's not for some. Actually, this is true for what? We're assuming it's true for what? Right. The statement is that T preserves all linear combinations, not just one of them, all of them, right? So then what do? We consider T of what? Sum I equals 1 to n plus 1, right, of ci vi for some set of constants and vectors in the vector space, right? And then what's the definition of this? Remember the definition of finite sum? We made it recursively, like this, right? So then what? So we can use additivity to do this, right? Which we have because T is assumed to be a linear transformation, right? And then what? Homogeneity on the first term, right? Homogeneity pulls out the Cn plus 1. But how about the second piece? What do we get to do there? Right, and why can I do that? Right, that's exactly my induction hypothesis, right? So my induction hypothesis is precisely that I can rewrite this as the sum I equals 1 to n of ci t of vi. But then, by definition of finite sum again, I have the sum I equals 1 to n plus 1 of ci t of vi. And that completes the proof by induction. So the linear transformation of a linear combination is, in fact, a linear combination of the images. Just language, guys. Not like Trump, but like mathematical language. So V maps to T of VI. So this is the image of VI under T, okay? If you're not familiar with that language, that's what that means when I say image. Any questions so far? Something that's almost immediate from what I've written so far is that if we feed a linear transformation a linearly dependent set, then its image. So let me just remind you the definition. If S is a subset of V, and T is like an element of, say, the functions from V to W, okay? So here, this is just functions. I don't assume linearity there per se. Just any single valued assignment of things in V to things in W, that's a function. There are many things in here which are nonlinear, right? Like L of VW is a subset of that, a very small subset. Anyway, given that, we can define T of S. That's the image of T, image of S under T. What this defined to be is T of X, such that X is an element of S. So this is the image of S under T. The image of a set. The image of a set is once more a set. Okay? What is it? Or something? Where the what? Is there a typo? Or is it just my bad handwriting somewhere?
I think the second to last. It was T of C n plus 1, and then the next line T is gone.
Oh, up here, I'm using additivity. So I've got like, basically this whole thing is like X, and this whole thing is like Y. So we've got T of X plus Y is T of X plus T of Y. It's additivity of T, that step. Yeah. I don't mind you guys interrupting me, ask questions like that. Like, that's always fine. So this is, the definition of an image of a set under a function. Okay? This? Yeah, it's a script F, like functions, just all functions. Here's a theorem. Proposition, what is it? I called it a proposition. If S is subset of V is linearly dependent and T is a linear transformation from V to W. Again, throughout this lecture, V and W are vector spaces over a field F, okay? Then T of S is linearly dependent. It's a linearly dependent subset of what, to be precise? Of W. How do we prove this? What does it mean to say S is linearly dependent? Implies that there exists C1 ck in the field, not all 0, right? Such that what? Well, sorry, a little bit more. Not all 0, such that there exists, S1 sk in the set S, such that what? Exactly. So sum of Ci, Si is equal to 0, right? Right. But by our previous theorem, I'll give it a name. I'll call it ghost. There you go. It's the ghost theorem for today. By the ghost theorem, part 2, right? We have T of sum over Ci, Si, right? I equals 1 to k is the sum I equals 1 to k of Ci, T of Si. And of course, T of Si are elements of T of S. Hence, star is a linear dependence of T of S. Oh, I'm sorry. How do I know that that's equal to 0? Oopsie. Got ahead of myself. I have cluttered it now. I'm sorry. What I should have said is, here I should have said 0 is equal to T of 0 is equal to that, right? I know 0 equal to T of 0 by part 1 of the Gauss theorem. But then 0 is equal to this linear combination of the s's because s is linearly dependent. But then I can use part 2 of the Gauss theorem to pull out the constants in the sum, and there you have it. It's a linear dependence in the image. So the image of a linearly dependent set is linearly dependent. That's what we're proving. So under a linear transformation, the image of a linearly dependent set is linearly dependent. I guess a natural question to ask paired to that would be what? What about linear independence, right? And I will get around to talking about that in its entirety, but I don't quite settle that question just yet. Well, I mean, I can tell you the answer. It turns out that a linear transformation will map linearly independent sets to linearly independent sets only if the function is in fact injective, if it's one-to-one. So our next thing to study is one-to-oneness, all right? Injectivity. Any questions about this proof? Okay. So how do you check if a function's one-to-one? Well, if you don't know that, you should go back and review. I'm just going to go on here. What's that? I'm sorry? Yeah. What does a vertical line test look like in a vector space of 3x2 matrices mapping to a set of up to fifth order polynomials? Like, how do you check the vertical line test for that? Theorem. Linear map T an element of L of VW. In other words, a linear transformation is injective. Injective, just fancy speak for one-to-one, right? If and only if the kernel of T is equal to 0. All right. You're like, kernel? What's a kernel? Good question. So let me make a definition for you, which I probably should have made before this theorem. Oh, well, it's too late. Look, this is the image of a set. What's the inverse image of a set? If we have let's say, U, a subset of W, then we can also talk about the inverse image of U under T. And what this is going to be is X in V such that T of X is an element of U. So the inverse image of a set, all right, it's the subset of the domain which maps to that set. I'll repeat that. An inverse image of a set, which is going to be the inverse image of something in the codomain, all right, is the subset of the domain which actually maps to that set. Okay, so-called inverse image. Now, this kernel of T, by definition, the kernel of T is simply the inverse image of 0, the set containing 0. So the kernel of T is the inverse image of 0. To give you a slightly more workable definition, what we're looking at here is V and V, or I'll say X and V, X in the domain, such that T of X is equal to 0. That's what this boils down to here. So there's your definition of the kernel. It's the set of all elements in the domain which map to 0. It's a very important subset associated with a linear transformation. In fact, what I'm just telling you in this theorem right here, right, is that if the kernel is 0, the function's injective. Before I prove this theorem, let me just give you a little side example. I mean, why is this special to linear transformations? Just a cautionary tale. If you look at f of x equals to x squared, right? So here we have f, a mapping from the reals to the reals. What's the inverse image? What's the inverse image of 0 here? X, such that x squared equals to 0, which is what? 0, right? So what you might call the kernel of this function is 0, and yet it's certainly not 1-to-1, right? You guys know it. The graph looks like this. Fails the horizontal line test miserably. You have a and b not equal, such that f of a is equal to f of b, but a is not equal to b, right? Or, as I like to look at it, a equals b did not imply that, oh, I'm sorry, other way around. I'll shut up. Anyway, that's obviously the danger of not having linearity. This isn't a test if you don't have linearity. Okay, so let's prove this theorem. It's an if and only if, right? So we got two directions we ought to prove. Proof. Assume that T is a mapping from V to W, is linear and 1-to-1, all right? If x is an element of the kernel of T, then what? What does that mean? T of x is what? 0. But 0 is also equal to what? T of 0 by ghost number 1. Consequently, by injectivity, right? So therefore what? The kernel of T is a subset of the set containing 0. And the converse direction is already true, right? Like, clearly, we already know that 0 is a subset of the kernel. So we have inclusion both ways, right? A is a subset of B, B is a subset of A. It follows then that A and B are equal as sets, right? This is how we prove equality of sets. We prove mutual containment. So hence the kernel of T is 0. Well, what did we just do? We just did this much, right? We did the forward implication. Now we need to reverse this. How about the other direction? Assume the kernel is 0. Then, to prove injectivity, I should say consider T of x equals to T of y. What's our goal? Our goal is to show that if the outputs are equal, the inputs must be identical. That's injectivity, right? Well, that's how I think about injectivity. Other people like to think about it in terms of not equalness. All right, so T of x equal to T of y. What can we do? That says that T of x minus T of y is equal to what? 0. And that, hence what? T of x minus y is equal to 0 by linearity of t. Therefore what? X minus y is an element of the kernel of t. See, I just showed that x minus y maps to 0. That means it's in the kernel, by definition of kernel. Any of you guys ever watch Monty Python? You ever seen that sketch where the mafia threatens the army about their tanks? Like, shame if anything happened to them, Colonel. Blah blah blah. Whenever I say Colonel, I always think of that. Now you're stuck with that if you also know what I'm talking about. It's a really bizarre thing to think about in terms of kernel. But anyway, I digress. My point to you anyway is you should know the definition of kernel. And whether or not you watch Monty Python, it doesn't really matter. Probably better if you haven't. Let's see here. So, but the kernel of t is what? It's 0, right? So therefore, x minus y is equal to 0. Therefore, x is equal to y. Hence, t is 1 to 1. This is an amazing theorem. It says that one-to-oneness can be just checked by calculating the kernel. That is such a precious, precious fact. All right. I have one more big theorem for today. Here it is. If we have t, a linear transformation from v to w, where v and w, again, are vector spaces over a field, and if we have subspaces, if we have v1 subspace of v, and let's say w1 is a subspace of w, then 1, t of v1 is a subspace of w. And 2, the inverse image of w1 is a subspace of v. This theorem is huge. I say that with all the rights and privileges guaranteed thereunto. I mean, wow, this is just amazing, amazing thing. I cannot overemphasize how important this is. Once you believe this, yes, sir?
What's the word next to linear?
Transformation, sorry. I could just be like, t is an element of L of VW and be done with it, right? So immediate application of this, before I get lost in the proof of it. An immediate application, it won't take long to prove either, don't worry. So how about this? The range of t is what? What's the range of t by definition? That's t of v. Well, is v a subspace of v? Trivially so, yes. So one of the implications of this is that the range of a linear transformation is a subspace of the codomain. That's wonderful. It's a beautiful result. Another implication of this is that the kernel of the linear transformation is a subspace of the domain. So you give me a linear transformation, I automatically get attached to it 2 special subspaces, one for the domain, one for the codomain. Very nice. Because, by the way, 0 is a subspace of the domain, right? The stupid subspace, the 0 subspace. All right, so how are we going to prove this? How do you prove something's a subspace? I think by now it has been drilled into you, yes? So we'll let x and y be elements of t of v1 and c an element of the field. What does it mean? That means that there exists, let's say, x bar and y bar in v1 such that what? T of x bar is equal to x and t of y bar is equal to y. Why is that? By definition, right? The image under v1 is the set of points which are mapped to under t by v1. Oh, I'm sorry. I need to write bigger in a different color. Or you guys need to get binoculars. I'll change to black. So I'm okay. So consider t of x cx bar plus y bar is equal to what? Right, c of tx bar plus t of y bar, which is what, by the way? Cx plus y, right? So all I said, for those of you who are in the far reaches of the room, fine. It was t of x bar equals to x, and t of y bar equals to y. What is this calculation I just wrote? What does this show? Therefore, cx plus y is an element of what? A little bit more leading question. Cx plus y, this is an element of what? This is an element of v1 again, right? Excuse me, this is an element of, uno momento, wrong thing. This over here is an element of v1, right? How do I know that cx bar plus y bar is an element of v1? v1's a subspace, right? So if x bar and y bar are in v1, then a linear combination of them is again in v1, because v1 is assumed to be a subspace. So I have, what do I have? I have the image of something in v1 is equal to this guy. So what can you say about this guy? It's an element of what? T of v1. It's in the image of v1. Which shows what? It shows that the image of v1 is closed under addition and scalar multiplication. How do I know that it's non-empty? 0 is an element of v1, right? T of 0 is equal to 0. So, that's an element of T of v1, which is not equal to the empty set, right? So it's a non-empty set closed under addition and scalar multiplication. Therefore, it's a subspace. Es bueno. Now, the proof of 2 always makes you guys a little bit more confused. But, oh, wait, well, we actually have time. I started 2 minutes late. I don't want to deprive you of your value. So, but any questions about that before I do 2? So 2. Let x and y be elements of the inverse image of W1, right? What's that mean? Then what do we get to say? T of x and T of y are elements of what? By definition of inverse image, those are elements of? No. The inverse image, oh, I'm sorry, yes. Fair enough. These guys are in V. That's true, but what I'm asking is T of x and T of y are elements of what? What's that? Let me write over here. So if x and y are elements of the inverse image under T of W1, right? Then T of x and T of y are elements of W1 by definition of inverse image, folks. That's the definition of inverse image right there. So then what? Let C be a constant in the field, right? What are we trying to show? We're trying to show that a linear combination of what? We'd like to show that what? T of Cx plus y is where? If I can show that that's in W1, what would that prove? would prove that this is in the inverse image, that cx plus y is in the inverse image of W1. Okay, so I use linearity. This gives me what? This is c times t of x plus t of y, right? Uh-oh, I think I got lost. Oops. Oh, I'm sorry. Oh, I'm not lost yet. So I'll get there eventually. How about this? T of x plus t of y. What do we got here? These are elements of the subspace W1, right? So this whole thing is equal to what? This whole thing is an element of W1, right? Because t of x and t of y are W1 elements, the linear combination of them is again a W1 element. But what does that show? Cx plus y is an element of the inverse image of W1. And again, you can show zeros in there. So therefore, it's true by the subspace test. With that, I will shut up. Hopefully Friday, I will show you more about standard matrices and that stuff. There still is a little bit more theoretical stuff I should probably tell you, but maybe I'll project it.